leaving the hardware industry and geopolitics wounded aside. As a data center hardware capacity planning professional, venturing into the world of AI, it's clear that the generative AI field is closely tied to computational power. Unlike traditional product development where R&D investment might not directly correlate with product value, generative AI benefits significantly from increased computational resources, resulting in better outcomes. Currently, the key driver in the industry is the cost associated with training and inference processes. Reports indicate a significant supply-demand gap in computational resources for AI, with demand surpassing supply by a factor of 10. This scarcity underscores the critical role of affordable access to computational power for the success of AI companies. It's noteworthy that some companies allocate over 80% of their raised capital toward securing adequate computing resources. Therefore, establishing a comprehensive framework to assess and manage the costs of creating new AI products, particularly in terms of compute resources, is crucial for navigating this dynamic landscape effectively. Generative AI's compute demand is skyrocketing, especially for transformer-based models. Costs for inference and training are tied to the model's parameters and input-output tokens, with tokens representing words or parts of words. Transformers' complexity drives memory and computational needs, making optimal hardware selection essential. Generative AI's success hinges on smart model sizing and hardware choices. A case for optimal AI infrastructure investment. In the realm of AI, the transformational power of generative models is evident. However, delving into the intricate details of their computational demands is crucial for data center hardware capacity planning. When we examine the time and cost aspects, it's apparent that the computational complexity is immense. Consider this: a single GPT inference without leveraging parallel architecture clocks in at around 32 hours on a standard processor core, making the need for specialized chips. NVIDIA. https www.cnbc.com/2023/08/NVIDIA reveals new iChips as cost of running large language models will drop significantly. HTML. AI models, including the widely used transformer-based architectures, operate on GPUs with dedicated cores. For instance, NVIDIA A100 GPUs boast 512 tensor cores, reducing the GPT-3 inference to about 1 seconds in theory. Yet, this simplification has nuances. Bottlenecks emerge from data movement, the weight's sheer volume, and optimizations, involving various floating point representations. To illustrate, the train-in-G transformer model takes about 3 times as long per token as inference, amplified by the colossal training dataset size. A single training run for GPT on A100 cards incurs costs of around $560,000. Considering compute rates, cloud-based training clusters are a practical choice. While GPU improvements and optimization attempts transpire, the colossal AI expansion overrides these effects. GPT inference costs fall between $0.0002 and $0.0014 for 1,000 tokens, making text-based AI use cases financially feasible. Training GPT is pricier, ranging from $500,000 to $4.6 million per run, driven by compute-intensive requirements. Despite advancements, AI infrastructure investment remains vital for optimal results. In this landscape, balancing compute capabilities, costs, and performance becomes paramount. And while GPUs are getting faster, and we find ways to optimize training, the rapid expansion of AI negates both of these effects. Everyone is a programmer now. You just have to say something to the computer. Quote, Economics of AI and the Chip Wars. External versus in-house infrastructure. When considering the future of our tech investments, the allure of GPU-powered AI hardware is undeniable. As tech enthusiasts, we're drawn to the control and power it provides for model training. Yet, in today's landscape, it's crucial to weigh the options between building in-house AI infrastructure and leveraging externally hosted model services. For startups, especially those in the app space, hosted model services like OpenAI, Hugging Face, and Replicate offer a compelling solution. They allow us to swiftly explore product-market fit without grappling with underlying infrastructure management. THSA services are becoming increasingly sophisticated, granting developers significant control over model performance through prompt engineering and fine-tuning abstractions. Their consumption-based pricing can often be more cost-effective than maintaining separate infrastructure, enabling startups to thrive. Conversely, startups focused on creating new foundational models or specialized AI applications might find running their models on GPUs essential. Whether the model itself is the product or fine-tuned control is paramount. This approach can provide a competitive edge. Striking the right balance between outsourced and in-house infrastructure is pivotal as we navigate the evolving tech landscape and strive for innovation. Navigating AI infrastructure, cloud versus data center as we shape our tech investments' future direction. The choice between cloud and data center deserves careful consideration. Generally, the cloud offers advantages like scalability, regional availability, and reduced upfront costs. It's a compelling choice for startups and larger companies, minimizing distractions from the data center setup. While the cloud is the go-to solution, exceptions exist. Reed was moving to the cloud a mistake? Scale. At a substantial scale, building your data center might be more cost-effective. Greater than $50 million per year spent. Hardware specifics. Unique hardware needs, like rare GPUs or unconventional memory, storage, or networking. Geopolitical factors. If cloud options aren't viable for geopolitical reasons. For those considering data centers, detailed price-performance analyses are available. Factors like GPU card cost, power consumption, space, and cooling play a role. Even seemingly similar cards can differ significantly in energy use, affecting total cost as we deliberate on this pivotal decision. Cloud computing remains the preferred route for most startups. Choosing the right cloud provider for AI workloads. Choice of cloud service provider holds significant implications. Major players like AWS, Azure, and GCP offer GPU instances, but new AI-focused providers are also emerging. Comparison of major providers. https://i1.wp.com, a16z.com/wp content. Uploads, 2 April 2023. Available GPUs by cloud provider.png. SSL equals 1. Here's a framework to help decision making. Price. While compute capacity is standard, prices vary remarkably among providers. Larger public clouds charge a premium for brand reputation, while specialty AI providers offer competitive rates through optimized data centers or cloud arbitrage. Negotiating prices is common, benefiting larger buyers, but smaller companies can secure aggressive pricing from specialty clouds. Availability. High-demand GPUs, like NVIDIA A100s, have been scarce. Surprisingly, Startups often find more available chips at small AR providers. NVIDIA's broad commitment to industry availability levels the playing field, allowing faster hardware access and potential cost savings through newer infrastructure companies. Compute delivery model. Major clouds offer dedicated GPU instances due to unsolved GPU virtualization challenges. Specialized AI clouds offer alternative models, like containers or batch jobs, potentially reducing costs by eliminating instance startup, teardown expenses. Network interconnects. For training, network bandwidth significantly impacts provider selection. Clusters with dedicated interconnects are essential for specific large models. Egress traffic fees are crucial for image generation. Customer support. Large clouds serve diverse customers. M-hacking support challenging. Specialized AI clouds excel with responsive support, focusing on AI-specific features and bugs, benefiting from their homogeneous workloads. Comparing GPUs, all else being equal, the top-end GPUs will perform best on nearly all workloads. However, the best hardware is also substantially more expensive. Picking the right type of GPU for your specific application can substantially reduce cost and may make the difference between a viable and non-viable business model. https a16z.com/2023/04/27/ navigating the high cost of iCompute. Optimizing GPU choices for your application as we navigate our tech investments. The selection of GPUs aligns with crucial technical considerations. Balancing the below aspects will help make informed GPU decisions aligned with the application's needs and cost effectiveness, driving our technical investments forward strategically. Training versus inference. Training LLMs demands substantial memory and high bandwidth connections between servers, favoring NVIDIA H100 or A100. While H100 might require longer-term commitments, A100 is more accessible for large clusters. Memory requirements. Large models require split-parameter storage across cards, necessitating setups akin to training. Smaller models like Stable Diffusion can utilize A10, A40, A4000, A5000, A6000, or even RTX cards, as they demand less VRAM hardware support. While NVIDIA is predominant, alternatives like Google TPUs and Intel's Gaudi 2 are gaining attention. Performance depends on available software optimizations, warranting POCs to gauge efficacy. Latency requirements. Less latency-sensitive tasks can employ less powerful GPUs for cost savings, up to 3-4x difference. User-facing apps necessitate top-end cards for real-time experiences, often requiring model optimization. For cost management, spikiness. The volatility of generative AI demand can be addressed with lower-end GPUs, leveraging readily available compute nodes, serving high demand but less engaged users with lower-cost resources can optimize expenses at the expense of performance. Strategies to optimize AI operations cost effectively. Maximizing AI operations efficiency requires a blend of software and model optimizations. Achieving up to 10x performance gains is feasible, but choosing the right techniques depends on your unique model and system setup. Broadly applicable techniques. Employing shorter floating point representations, FP16, FP8, or quantization, INT8, INT4, INT2, can linearly enhance speed by reducing bits, sometimes involving model adjustments. Automating mixed or shorter precision is increasingly feasible. Pruning neural networks by ignoring low value weights combined with Efficient sparse matrix multiplication boosts performance on modern GPUs, addressing memory bandwidth bottlenecks through weight streaming. Also helps model-specific optimization. Some optimizations are tailored to specific models. Notably, Stable Diffusion has reduced VRAM needs for inference, showcasing model-specific advancements. Hardware-specific optimization. NVIDIA's TensorRT includes hardware-specific optimizations but is confined to NVIDIA hardware. Effective task scheduling. Task scheduling significantly impacts performance. Allocating models on GPUs to minimize weight swapping. Selecting the best GPU if multiple are available. And batching workloads to reduce downtime are key practices. Leveraging third-party expertise. Model optimization remains intricate. Many startups collaborate with specialized optimization companies like OctoML or SegMind. WHIC focus on tailored enhancements for generative models. How will AI infrastructure cost evolve? Over the last few years, we have seen exponential growth in both model parameters and GPU compute power. It is unclear if this trend will continue. There is no sign that the GPU shortage we have today will abate shortly. Will this continued high cost of AI infrastructure create a moat that makes it impossible for new entrants to catch up with well-funded incumbents? We don't know the answer. Over time, the cost structure of the emerging AI software stack may start looking more like the traditional software industry. And that's a big guess. Even AI cannot predict this.